So I'd like to welcome everybody to this edition of the Western Hemisphere Colloquium on Geometry and Physics. As always, the talk will be an hour, and during the talk, if you have any questions, please use the chat and send your question to everyone. Sometimes other people in the audience answer, and occasionally the speaker will answer those questions. And certainly after the talk, we'll have a Q&A. So you can raise your hand using the raise hand in the participants panel, and then I'll call on people as they raise their hand. So today we're very happy to have Djordje Radicevic from Brandeis University, who will talk about the lattice-continuum correspondence in quantum mechanics.
Thank you, Dan. Thank you everyone for inviting me. It's an honor to speak at this seminar series. Thanks for the care in the introduction as well. So let me just start. And I would like to start by explaining my title. This explanation will actually take several slides, so it will also conveniently serve as an introduction to my talk. So please let me know or if there are any technical issues, and I will periodically stop to ask if there are any questions, which I understand will be forwarded to me. Okay. Okay, perfect. So this works. So I want to start by explaining what I precisely mean by the words lattice and continuum when talking about quantum field theories. These are essentially two very different frameworks for thinking about quantum field theory. And I think a fair way to describe them is as follows. So when I talk about a continuum QFT, I have a setup like this in mind. I have some manifold, and I have some assignment of operators to parts of that manifold. Points, lines, surfaces, maybe even the entire manifold, etc. And then I have also the dynamics of this quantum theory, which is essentially some self-consistent set of rules which allow me to assign expectation values to operators and to products of operators. So different continuum theories will have different rules, of course. They may depend on different structures of the underlying manifold. They may or may not depend on the metric of the manifold, etc. And the operators I choose to work with may be chosen to furnish representations of different symmetry groups or other more general algebraic structures. So this is a very general way of describing a large class of theories. This includes topological field theories. This includes conformal field theories. This includes perturbative quantum field theories of the kind you learn in textbooks, and so on. So the class of continuum QFTs, as I will talk about them here, really contains, most perennial favorites. On the other hand, lattice QFTs are something very different, and I will have a very specific meaning of the phrases I've shown here. So to define them, take a graph, a finite, possibly very large, but finite graph. So you can call it a lattice, if you will. And to parts of this graph, to certain parts of this graph, associate finite dimensional Hilbert spaces. So you can associate some these Hilbert spaces to points, to links, to faces, etc. So to different elements of this graph, and then the total Hilbert space of the entire field theory, of the entire lattice field theory, will then be just a direct product, possibly graded, of these individual Hilbert spaces. And similarly, you will obtain operators in the theory by just taking possibly graded direct products of individual operators. So that sets up the kinematics of the lattice field theory, and the dynamics is completely supplied by a single operator of this algebra of operators called the Hamiltonian. In this setup, it's just a possibly huge but finite matrix. So everything is completely regularized in this setup. Everything is completely finite. And possibly large, as I said, but everything is very explicit. So both frameworks have advantages and conversely disadvantages. So continuum theories, like the continuum framework is, I hardly need to extol its virtues. So it's connected to a vast trove of mathematical structure. It gives rise to many interesting ideas, theorems, even insights into pure math. And also, luckily, it also is very, very useful for describing our own world, for calculating things that are later confirmed in experiments, in accelerators, etc. So it's very useful in many ways. On the other hand, the lattice framework also has uses. One of them, a very concrete use, is the fact that we can actually put it on a computer and we can simulate it. So we can actually understand it in much greater detail in some senses than we can ever do in a continuum theory. Similarly, we can simulate it. We can actually build experimental apparatuses which actually simulate a lattice field theory out of a finite number of spins or electrons or lasers, etc. And finally, what sort of drives my talk and the entire project, the entire set of ideas that I've been playing with for the last year or so, is the fact that these lattice field theories are very, very easy to define. There are no pathological examples. There are no degrees of well-definedness that one often has to wrestle with when talking about continuum field theories. So everything is very explicit and in simple-minded, if you will, and that has its charms, as I will try to explain further in this talk. So these are two different frameworks, and they are natural. Each is natural for describing certain phenomena and less natural for describing others. It may be possible to talk about the same phenomenon, the same QFT phenomenon in both, but very often things are much more natural in one than the other. So I will not talk much more about these particular examples, but some elementary examples are listed here. So for instance, it's comparatively quite easy to talk about chiral theories in the continuum, whereas thinking about them on the lattice has always been a kind of stumbling block. On the other hand, lattice theories have a very, very sort of natural onset of confinement. It's very easy to understand what it means when a gauge theory on a lattice is confined. It's much more difficult to talk about this in the continuum. Of course, it's possible, but we still have a lot that we do not understand. So there are many puzzles about the connection between the two frameworks, and the one I want to focus on here is as written. So I want to understand whether it is actually possible to come up with a lattice formulation for essentially every continuum quantum field theory. Can we find a sufficiently large lattice which at long distances and with appropriately tuned couplings, etc., actually displays any desired continuum behavior that we can get from other continuum methods? That's a puzzle that, as far as I know, we do not have an answer for. It's sort of a matter of taste whether you believe the answer is yes or no. But even in cases where we kind of do understand how individual correlation functions of a continuum theory do arise from a lattice, like for instance in StatMech models in 1+1 dimension and so on, it's still difficult to understand how the entire continuum structure of a continuum QFT emerges from the lattice, because there's more to a continuum theory than just a few correlation functions. There are algebraic structures, there's operator product expansions, there's current algebras, there are various anomalies, and so on. There are many concepts which exist in the continuum language which are sort of very unnatural in the lattice language. And so one would like to know how would these things emerge, ideally in some controlled way from a lattice. So this is the kind of question I've been thinking about, and in this talk I want to essentially answer it in detail for quantum field theory in 0+1 dimensions, also known as quantum mechanics. So there are no spatial dimensions. Everything that happens is the theory is essentially the theory of a single quantum particle moving in some target space. So that's the question. This is still there's still a lot of stuff happening. This step happening even in this simple setup. It's definitely not a trivial situation. So there's a lot that we can say about it, and I think it's a good introduction. I will mention near the end, perhaps, how to generalize certain things to higher dimensions. Some of it has already been done, or I have already done some of it, and there's a roadmap to how to generalize to higher dimensions. But this talk will be pretty firmly in 0+1. So let me clarify. When I talk about lattice quantum mechanics, what I mean by that is that that I just have a finite dimensional Hilbert space. So another way to say it is that the target space on which my quantum particle moves is finite. So for instance, it can be zk, which is of course the cyclic group of order k in the physicist notation. And then conversely, when I talk about a continuum quantum mechanics, I will mean the quantum mechanics of a particle moving on some n-dimensional manifold. So for instance, Rn or an n-sphere or something like that. And here I will just focus on n=1. So I will focus on one-dimensional target spaces. So in particular, I will focus on how a theory of a particle moving on R or on a circle, S1, emerges from a lattice theory of a particle moving on a zk target space with a sufficiently large k. That's the goal, and it may sound simple, and a lot of the stuff that I do will sound familiar and simple, but there will be some crucial ingredients which have not been present in the literature, at least to my knowledge, and that are new, and that will then pave the way to understanding how to do this in higher dimensions too. So finally, as the sort of ending of my introduction, I want to take a step back and ask myself why I'm even asking these questions. Who cares about this lattice-continuum correspondence at all, and why should you care? And my answer would be as follows. So there are essentially two answers I can give. One is a sort of simple aesthetic answer, which is that I really would like to understand what's the relation between these two divergent viewpoints on QFT. I want to know whether they're really describing the same object or different objects, etc. And then I think that thinking along these lines actually has utility in sort of paving the road to new definitions and proofs, which are just as rigorous and potentially just as useful as the existing ones in the continuum. So two recent papers that I've put out I guess at the very end of last year, do this in 1+1 dimensional QFT. So for instance, it's possible to start from a lattice and sort of embed abelian Gaussianization in 1+1D into a lattice framework, and therefore essentially prove it together with bounds and when it's valid and so on, in a way that it was, let's say, never made this precise. Another thing you can do is you can actually start from a lattice and just derive OP coefficients in a conformal field theory from scratch, without assuming anything about there being conformal symmetry or something like that. So these are nice things. So it sort of gives you an idea how these continuum things, these dualities and operator product algebras emerge from the lattice, and sort of gives you new ways of defining them. In this concrete talk, I will also show how one can think about continuum quantum mechanics as something that emerges from a lattice, which is easily defined. So I will never have to, work with functional analysis. I will never have to work with, very complicated operator analysis, and yet I will still be able to talk about many objects of interest. So I think that's nice, especially if you're a physicist and find functional analysis difficult. And then, of course, there's the fact that this will also pave the way towards understanding other theories, towards understanding how other continuum theories can be given lattice representations. Because we definitely have continuum theories for which we have no idea how to laticize them, how to give them any kind of non-perturbative completion. Gravity is perhaps the ultimate example. There are, of course, individual counterexamples, but in general, Einstein gravity is a good example of a theory for which we do not have a good lattice completion, especially in a canonical formalism. So this is sort of the goal. So let me pause here before diving into details, and I see that there are some questions, so I guess I can ask.
Yeah, so are you discretizing time or space?
Good question. So, well, I'm in 0 + 1 dimensions. So in some sense, first, there's only time. So there's time, and then there's the target space.
Correct. And which one are you discretizing?
Both, but the most important one is the target space that I'm discretizing. And so this will become clear when I give you the outline, which I guess I can just do now. So, so the idea is that first I will be in the canonical formalism, where there's only the target space to talk about. I'm at a constant time slice, if you will. And there I will talk about only what it means to discretize just the target manifold. And then I will formulate the same story using path integrals. And then there will be the extra quirk of being able to discretize, or having to think about the discretization of time as well. So the primary object is going to be the discretization of the target space, but I will also talk about the discretization of time as well. My primary way of thinking is always canonical. So in that sense, in that language, there's no time per se.
But in the higher dimensional examples you had on the last slide, you would discretize space-time or the part of it.
Yeah, good. So in the higher dimensional examples, I would discretize both the target and the spatial manifold. Again, in the canonical formalism, I would not say anything about time. And then I could write down a path integral, and then I would also have the additional discretization of time, which can in principle be different from the discretization of space.
Okay, thanks.
Should I answer anything else right now, or should I focus on this? Can I continue?
There's one more question that says, so for instance, we do not have an SU2 spin quantum mechanics, but a discretized version. That's a question.
Right. So if you mean that, if you mean SU2 as in a particle moving on an SU2 manifold, like a 3-sphere, then yeah, like I would want to replace that with a discretized version too. I will not be working with that in this talk because I said I will only be working with one-dimensional target spaces. But in principle, yeah, like there's, as far as I can tell, there's nothing fundamentally different from extending to higher dimensional target spaces and talking about nonlinear sigma models in the same way. It's just going to be slightly more difficult.
Why don't you go on then? Thanks.
Okay. So I kind of already revealed the outline. I'm roughly envisioning three parts. And there's a 20% chance I will actually have time to finish to cover the third part. We'll see. The first part is going to, as I said, deal only with the canonical formalism. So I will be at a fixed time, and I will talk about operators. I will talk about operators that figure in the theory of a quantum particle moving on a ZK target space. And I will describe two elementary procedures called smoothing and Gaussianization that essentially restrict the algebra of operators of this lattice theory, of this lattice quantum mechanics, to a sub-theory, to a smaller algebra that corresponds to a sub-theory, in which is essentially going to behave in every way as a continuum theory. So provided that, you know, the k in zk is large enough and that certain other parameters are appropriately chosen, I will have you know, essentially an Ersatz continuum theory here. So it's a sort of a spiritual successor to Wilson's renormalization group. So that takes away stray degrees of freedom in some sense and gives me only the continuum ones. So that's part one. And then part two, I will describe how to do the same thing in the path integral formalism. Except there, of course, there's the fact that there's also the time direction, and there will be and I will have the ability to also perform the smoothing procedure, which I will explain, along that temporal direction as well. And this will turn out to be a sort of something that does not have a canonical counterpart. It sort of mutilates the path integral. It's not a controlled approximation that gives me, you know, a path integral in a one-dimensional spacetime with smoothly varying functions everywhere. And but it's really this step which will give rise to all the interesting concepts, like, for instance, dilatation symmetry that I will talk about later. So I will discuss when you are justified in doing this extra step when working with path integrals. And then finally, as I said, time permitting, I will discuss fermions, and I will discuss coupling fermions to a bosonic theory in such a way to get a supersymmetric lattice theory. This is totally elementary in some sense. Like it's just something that may not have featured very much in the literature in this language, but essentially I can come up with a lattice version of a supersymmetric harmonic oscillator with ease. I can also describe even simpler toy models which have supersymmetry. And I will also, if I have time, I will stress that all lattice models which have supersymmetry must also have vanishing Witten index, meaning that the ground state has to be at least doubly degenerate. If I do not have time to prove this or discuss it in more detail, then at least I gave you the statement now. It's a kind of version of fermion doubling that you can prove.
Seem to be having some technical difficulties. So let's hope Djordje reappears.
Hello?
Yes.
Oh, I have no clue what happened. Both of my Zoom apps crashed on both of my devices.
Okay.
I don't know if, yeah, okay. Apologize for this. I have no idea what was going on. But yeah, let me share my screen again, I guess. You just need to make me a co-host again then.
Trying to find you. Actually, Ron, you're going to have to do that. Okay, should be done now.
Done. Yeah.
Okay, thanks. Yeah, sorry, this has never happened before, but there's always, okay, there's always the first time for these amazing things to happen. Okay, everything seems to be in order now, so let me continue. Okay, so the first procedure I want to talk about is called smoothing. In one sentence, what I want to do is to start from a lattice theory and come up with a appropriately truncated lattice theory in which wave functions have to be smooth as functions of the target space position. But let me describe in more detail how this goes. So let me start with lattice quantum mechanics with a k-dimensional Hilbert space that's spanned by these points on the unit circle that you see here. This should work. Yeah. So so these are evenly spaced points labeled by this straight phi with distance between them 2 pi over k or d phi. So we can assume that k is large, but for this first part, that's not even a necessary assumption. Good. So the algebra of operators that act on this quantum system is nicely thought of as being generated by two operators, the clock and the shift operator. They have many names, and one of the first places where their usage has been stressed was this paper by Schwinger, which I cite here. And these are just position and momentum operators in some glorified way. So they just either measure where you are on this clock, on this unit circle, or they move you by one notch on it. And then there's a natural model that you can think about, which is essentially a free particle on this clock, which either hops one step left or right or stays in place. And you can diagonalize it by going to this natural momentum basis, whose members are given here. And this P is what I will call the momentum. There's no spatial direction here, so I can just call it momentum without specifying anything further. It's some integer between which I choose to go from minus k half to k half. So far, so elementary. And then I will define the smooth subspace of this original Hilbert space as the set of just the low momentum states. So I will need to introduce a second cutoff. Let's call it PS. And at this point, this only really makes sense if k is large, so that I can define something like this. If not, then this is kind of meaningless as an exercise. I can still maybe define it, but it's not going to give me good results. So that's a smooth subspace. And then what I call smoothing is a projection from the original algebra of operators, which is essentially the algebra of all k by k complex matrices, to a unital algebra, which just preserves the smooth subspace. So there are a few choices that we can make. They don't matter that much for the purposes of this talk. So let's just imagine that we, in momentum space, in the momentum basis, we restrict each operator to 2ps times 2ps block corresponding to these low momentum states, and then we allow just the diagonal to exist outside of that. So this defines a projection that's given here. So you project just down to your projection to these smooth operators, the smoothness preserving operators, does not change any of the powers of x, the shift operator, but it does change z. It changes all powers of z in principle. And the important thing that I really want to stress is that it does not commute with taking the product of z's. So So especially, for instance, if you take P1 is equal to minus P2, you will see, on one hand, you will have the identity, which is obviously preserved under this smoothing. And on the other hand, you have two other operators which are not preserved. So basically, this kind of projection defines a second notion of what a product of operators can be. So I can either define a product of smooth operators by just multiplying them as matrices, or I can define a product of smooth operators as sort of first having multiplied them in the microscopic regime, in the original algebra, and then projecting. And it's really this which is going to give the richness of operator products that we may expect in a continuum theory. So far, this is pretty elementary, but we're getting to something non-trivial here. Next, I can do a second restriction, which I will call Gaussianization. A bit of an maybe unfortunate name, but I think it has its uses. So the subspace, this smooth subspace, I can also choose a different basis for it. I can choose a basis of smooth position states, which are defined as you see here. So basically, they're just I'm just performing the inverse Fourier transform, but now I'm forcing the momenta to only go to this new cutoff, to this new PS cutoff, not all the way to K half or something. So there are only two PS independent vectors, e to the I curly phi. And you can imagine them as being just smearings of the original e to the I straight phi states. So you just, instead of thinking of them as living on like a point or a tiny angle d straight phi, you can just imagine them having been smeared over a much larger angle d phi, d curly phi. So this is another useful basis, and it will become even more apparent as we go along. But for now, let me just plow on and formally define a second subspace. Now, so a subspace of the subspace, and call it the Gaussian subspace. Basically, it's the span. It's spanned by just these smooth vectors here that are within a certain angle, so that are, let's say, not too far from zero. So these curly phis can go, can take order 1 values. They can go all the way around the circle. They just move in a larger step than the original variables straight phi. But now let's say I also restrict them in their span like that. So you kind of see where I'm going. So the first one, in the first step in smoothing, I restricted to just low momentum states, and now I'm restricting to sort of small fluctuations around a certain point. So the remaining states are what we may call Gaussian states. They're sort of localized in both position and momentum space. And the corresponding projection is now less trivial to work with, perhaps a little bit less trivial to work with. In particular, it doesn't leave either operator invariant. You kind of have to worry about both shift and position shift and clock operators becoming something slightly non-trivial after you project. But in principle, you can still have explicit control over everything. And importantly, again, now for generic operators, it is still true that a product of operators before Gaussianization is not the same as the product of Gaussianized operators. That's sort of a fundamental thing, which will be important for deriving things like canonical commutation relations, as you may foresee already. Let me make a few remarks that might clarify what's going on here. So as I mentioned already, smoothing restricts to a set of states that vary slowly in position space. So if psi of phi are my wave functions in position space in the original basis of positions, then any state in the smooth subspace has to obey this, if you will, constraint on the wave function. So this new parameter PS that I have introduced really controls the derivative expansions. It says that no derivative can be larger than a certain there's a certain bound set by PS or PS over K rather. So so that's sort of the important thing here. And then, as I already said, also Gaussianization restricts the set of smooth wave functions further to smooth wave functions that are only supported on some, let's call it a compact set on some interval from minus phi g to plus phi g. Of course, you can shift that interval, you can change the definition a bit, you can play around with that, but you see where this is going. So after smoothing, your smoothing is enough to actually get you an Ersatz continuum theory, which effectively behaves like a quantum particle on a continuum S1, like on a smooth circle. And then if you want to talk about a quantum particle on R, you actually have to perform both of these restrictions. You have to Gaussianize, not just smooth, starting from ZK. And a slightly more mathematical comment is that this hierarchy that you need to define a Gaussian state, starting from some completely normal lattice thing, is in some way very close, mimics what's called the rigged Hilbert space construction, or the Gelfand triple in Russian literature, that you can find in many books as the rigorous foundation of quantum mechanics. So there you take some operator delta, and you come up with this hierarchy that you see here at the bottom of the slide. So you have this is quantum mechanics on R. So you start from a set of square integrable functions on R. You define a set of smooth functions, or differentiable in some sense, the domain of some differential operator delta. And then you also define a set of distributions, or a set of things that you can integrate against smooth functions and still get a finite answer, even though these things here might not necessarily be square integrable on their own. So this hierarchy is actually very similar to what I've come up with here. So in some sense, you go from both compact and smooth to just smooth to neither necessarily. Except, of course, everything I have done is on the lattice. So in that sense, you don't have to deal with defining what you mean by a bounded operator or unbounded operator, or what exactly is the measure on R that you take, etc., etc. But yeah, like in some way, what I'm doing is mimicking this old construction. And before I go into further details on, let me explain why this is even useful, because I kind of haven't stressed this yet. I just sort of gave you a bunch of formal definitions. So the real use of these reductions lies in the situations where there exists an energy eigenspace of your starting Hamiltonian, which is invariant under these projections. So if your Hamiltonian has smooth and Gaussian eigenstates, then these projections can be seen as sort of reducing just to that one theory, which then unitarily evolves with some effective Hamiltonian of its own. So and that sub-theory that you get to is going to be, for all intents and purposes, your continuum quantum mechanics with smoothness and compactness specified precisely by these parameters PS, K, and phi g, which I've defined along the way. And you can do this for any Hamiltonian. In the particular model Hamiltonian, the free model that I've been talking about, all energy eigenstates are invariant or smoothing. So it's sort of a very simple example, and none are invariant under Gaussianization, which really means that you can start from a free clock model. You can reduce to you can choose any PS and reduce to an effective theory of a quantum particle on a circle, but no choice of parameters will get you to from the free clock model to an effective continuum theory of a particle on a line. And one way of this is one manifestation of the old, completely well-known quantum mechanics 101 statement that if you have a free Hamiltonian on R, it has no normalizable eigenstates. Your eigenstates are going to be, e to the I px, and these are not normalizable functions. So that's this is how you start from a lattice model and sort of figure out whether it gives you a perfectly nice theory with normalizable, a continuum theory with normalizable eigenstates, or a theory with some pathology with non-normalizable eigenstates. If I started with a different lattice model, like something with a potential, then I would have gotten a theory with a non-trivial, with a bunch of low energy eigenstates, which are also invariant under Gaussianization. And then, then I would have had a perfectly well-defined quantum mechanics on R. For instance, I can get the harmonic oscillator that way. And let me comment again that if an invariant eigenspace does exist for under Gaussianization, then it is natural to define these operators P and Q that you have that I defined here. You can define them in slightly different ways too, but this is a useful choice. And then you can show that, of course, these operators obey the standard canonical relations that we always expect to see in quantum theory, in quantum mechanics. So P acts after Gaussianization, P acts as a derivative, and only after Gaussianization. Before, it doesn't act just like as a derivative. Q acts as just a linear multiplication by the position phi. And most importantly, their commutator acts as the identity matrix times I. It's crucial that we multiply them first and then Gaussianize, because if you were to, because there are no matrices whose commutator is the identity matrix. It's impossible because the commutator has to be traceless. So, so you had to always do this. Oh, okay. So I was going to stop for questions. I just saw a question by Greg Moore, but I guess this is the right time to stop for questions anyway. So
well, you can answer that one.
I didn't read it fully. I just saw it flashed on my
okay.
screen, so I wasn't sure what it said exactly.
His question says if the partial of is partial hat phi, wherever that is that a discrete derivative?
The answer is not quite, and I was kind of being a little bit coy here. So this is essentially something which, if you go to positions, if you go to momentum space, this is the operator which multiplies the momentum eigenstate P with the value of P. So it's something that if I were to expand this e to the I phi back in this basis here, it would just this d hat would just multiply it by P here, or minus I pi minus IP. So it would act as a discrete operator except at the edges of validity of this Gaussian space. So there are some caveats. So it acts as a discrete derivative only at really small values of phi, but it acts as a multiplication by P in momentum space at all P.
Okay. Maybe in the interest of time and letting you get forward with your talk, there's one more quick question now,
okay.
Which is, what do you mean by flow?
Okay, so it's I essentially mean something like an RG flow, where you go from some theory which is unitary to a theory which is also unitary. So like a map between two unitary theories. In general, these projections need not land you on a unitary theory. Like, for instance, if you Gaussianize the free clock model, you will land on a theory which, as I said, in which no energy eigenstate is pure. You will you will make all the energy eigenstates mixed. And that theory, that's not like a well-defined quantum theory on its own. So when I talk about a flow, I really mean a map between two unitary theories. That's all. Like, I'm not referring to some fancier word from the literature or something like that.
Okay, well, go ahead.
Thanks. Okay. So let me say more about how this entire spiel works in the path integral language. Here we have the thing that we want to calculate is typically a thermal partition function. So this first line is something that everyone has seen, I'm sure. So this is the definition of a partition function, and then you just expand it by inserting a bunch of decompositions of unity. And by doing so, you introduce the small parameter d tau, or a large parameter n0. So that's another knob you get to turn. That another thing you have to keep track of. So typically, when we do this, when we construct a path integral, we insert a complete or an overcomplete set of states at each time tau. If you insert an overcomplete, that gives you coherent state path integrals. The standard situation is to insert a complete set. The way that you implement smoothing in path integrals is you insert an undercomplete set. So you basically, instead of these weird phi's, you insert for these weird phi's, you insert just the smooth position states, nothing else, or low momentum states, if you wish, in the momentum basis. So this makes sure that your path integral will only ever sum over appropriately smeared position states, that essentially your trajectories are appropriately smeared along the target space at every time. Now you may wonder, okay, so when is this even allowed? This will cause some errors to happen, and indeed this is true. So this the new smoothed partition function that you get by having just an undercomplete set of states will only approximate the exact result in a regime that looks vaguely like this. This is a kind of dumb bound that you can easily derive by essentially exactly solving the theory. There must be better bounds. I just have not tried to optimize them. But what I want to stress, so basically it says that if you go to high enough temperatures, you can no longer just, of course, use smooth states in your smooth trajectories in your path integral. When I say smooth, again, I mean smoothly smeared over the target space. The important thing is that this bound depends on both PS and K. So a standard thing you might have done before is to say, oh, it's some bound that depends on just the lattice spacing. It actually doesn't depend just on the lattice spacing. It depends on both the lattice spacing and on the new cutoff PS. And the bound is actually kind of non-trivial, in fact. And there's probably an even less trivial, sharper bound. And another thing I want to stress is that as your temperature rises, so that the inverse temperature beta gets to this sort of cutoff level, then you have something that is very reminiscent of what lattice gauge theorists in the 70s and 80s called the roughening transition, appropriately named, given my language here. It's essentially a statement that, before, in lattice gauge theories, this was a statement that even before you hit confinement or an actual phase transition, as you increase temperature, or deconfinement rather, as you increase your temperature, you start seeing jagged fluctuations of electric fields, jagged configurations of electric fields. And that's very little is known about this particular thing. Like in some kinds, I don't know the exact history of it, but this is a sort of quantum mechanical manifestation of it. And so if you were to look at how the phase diagram works, you would see that there is this crossover, not exactly a phase transition, I would call it a crossover into this regime where non-smooth states start contaminating your partition function. So that's one thing. So first of all, you cannot compute high temperature partition functions using smooth fields, smooth trajectories. So it's bound to break down. And then there's a second bound. If you want to actually usefully compute the path integral, you have to have this other bound that I wrote here, and only if that kind of bound is satisfied. And again, notice that the bound uses PS, not K, so it doesn't use the smallest possible spacing. It uses the second scale. Only if that bound holds can you turn the crank that as you were taught in elementary school and get the standard path integral with the quadratic action here. So otherwise, you will get derivative corrections that scale with PS if PS is not sufficiently small. So this is something that this is a second bound that you need to keep in mind. If you want to get the the elementary school answer, you have to have this second bound on PS, or if you wish, a second bound on d tau. And then you want to go ahead and evaluate these integrals, because that's what we are taught to do, and that's really how we can really solve many theories. So the standard idea is to just Fourier transform, of course, and integrate these modes one by one. Now the problem is that the obvious problem is that because the field is compact at each time, the Fourier modes will not be independent variables. We can't just integrate we can't just do integrals one by one. And anyway, even if we could, then the product over Matsubara frequencies, or if we pretended we could, the product over Matsubara frequencies would be intractable. It would have these complex phases which oscillate really fast at high frequencies. So it will be a nightmare. So here, this is the standard solution to this problem, which of course, the end result is familiar to absolutely everyone who's done quantum field theory, but the lattice origin is a bit less familiar, I would say, or completely unknown. So the first thing you can do, which is a controlled approximation, is to just notice that the path integral is only dominated by configurations near saddle points. Fair enough. This is something that you can do, and in particular, you can convince yourself that this is a good cutoff to choose. That if you choose to keep only configurations that are this close to to a saddle point, you will actually get the right, approximately get the correct answer. Then the second thing is completely uncontrolled, and the second thing essentially says just discard high frequency modes, just linearize the spectrum. So basically, it's a projection that says start from your individual fluctuations, delta phi of tau, Fourier transform them, and then just remove all the high frequency modes. So get down to these new objects, delta phi of tau, where we've inserted yet another cutoff that I call NS. So this is what I call the temporal smoothing. As I said, it's not an approximation. It will never give you something approximating the right answer. It will really violate your theory, and it's really amazing that it's the miracle of renormalization, which says that even after you're temporally smooth, you will get something. You will get some ugly look, some expression from which you can extract, if you're powerful enough, you can extract the universal part, and that universal part will match the sought after answers yes, or at least the universal part thereof. So I will not go through the details of how to do this renormalization. This is the stuff that you can read in any condensed matter textbook. How to get from this sum, where this is an infinity here. How to go from a sum like that to to a universal answer. Oh, sorry, a product like that to a universal answer. But I want to specify that from a lattice point of view, this is a completely unreasonable thing to do a priori. But it's important, and it's important to be aware that you're doing it, and it's important to be aware of its possible limitations. So just two examples of the consequences of the fact that you have to do temporal smoothing to actually evaluate the integral. Or the fact that you have temporal smoothing as a thing. So one thing that I will stress is that many things that we talk about and take for granted in continuum field theories only really make sense in the continuum and not on the lattice, and it's really the temporal smoothing which allows you to make sense of them. One simple example are dilatations. So if I were to start with these objects delta phi of tau, that are sort of defined at discrete steps of time, tau. And I wanted to define a dilatation transformation on them. That's actually kind of completely nonsensical, because I would, lambda could not be a real number, because lambda tau needs to be another, integer multiple of d tau. I am not allowed to just rescale things randomly. So I would only be forced to work with, integer numbers of lambda, and even then the mapping would not be 1-to-1 or anything even close to that. It would be some mess. So this is really a completely insane transformation to try to do on a lattice. But once you have appreciated the need to start from the lattice and do temporal smoothing, then you can actually notice that this transformation is perfectly sensible, because the point of temporal smoothing was that just the same way that canonical smoothing worked, this guy here can be expanded in powers of tau, and you will get something that looks like this. So something that is only defined in terms of individual values of delta phi at tau. So that's the and you will have a similar thing if you want to talk about reparametrizations, which is as of like the last 3 years or so, like a very popular thing to talk about in quantum mechanics. I will not talk about that, but if you want to start from a lattice and and work your way up to conformal symmetry or reparametrization invariance, you actually need to perform this temporal smoothing. Another thing, and I'm nearing the end of the part that I have allotted for this talk. Another thing that you have to be very careful about is what happens when you start calculating 2-point functions, because there, if you start from a microscopically defined 2-point function with operator insertions at some points 0 and tau, let's say, then temporal smoothing means that you need to smooth both those and the modes that are in the action. So that means that you will have 2 different kinds of deviations from the exact answer when you just discard high frequency modes. So the ones that you've discarded from the action will give you an overall multiplicative difference from the exact answer. That's what's covered by counter terms. That's the lattice origin of counter terms, if you will. But you also have another set of terms that come from projecting out the high frequency modes from these operator insertions here, and those cannot be compensated by an overall rescaling by a counter term in the action. Those actually have to be compensated for by what you may call contact terms. And in quantum mechanics, it turns out that at least in these simple examples where I've been toying with, these contact terms do not have a universal piece. They're always dependent on various cutoffs, NS and PS, and that I've talked about. But in general, in higher dimensions, you may indeed find that these terms, and you will indeed find that these terms have also universal parts as well, which are of course of interest, and there has been work done on these things as well. So just to summarize, and I will now stop and take questions. This entire story was designed to start from a completely finite lattice theory, large but finite lattice theory, and to describe certain procedures which you can do to it to get something to get some new theory which is also finite but whose basic operators and basic variables really behave just like continuum ones, to a specified precision set by these cutoffs, by these various cutoffs. So there are a total of between 2 and 4 cutoffs, depending on how far you want to go. But basically, the point is that you're never satisfied with just a single cutoff k, or you always need to have at least one more to get to the continuum, this PS thing that I talked about. So in general, in higher dimensions, you will also have the same phenomenon. You will have more cutoffs that control derivative expansions. You make, I kind of flippantly call them string scales, but they're not necessarily exactly the same as a string scale. But yeah, the point is that you can always go from a lattice by appropriately truncating it to something that's very much like a continuum theory, even though it's perfectly well defined and flows directly from the lattice. But you just have to be aware that there are several other cutoffs that you need to keep track of, not just the original cutoffs, not just what you would normally call the lattice spacing, but also these other scales, PS and phi g and ns. So something that controls the compactness and smoothness in your target space, and something that controls the smoothness in your temporal direction. So with that, I want to sort of conclude by saying, okay, so this actually gives you a way to think about all of the continuum things that that you may have tried thinking about earlier from a completely nice finitary perspective, which certainly would be nice if you wanted to simulate them, but also it sort of promises that maybe there really is something to it from qubit where you can actually precisely start talking about continuum theories from lattice ones. And this is something that I think was not appreciated, how precisely it can be done. And I kind of want to get this idea out there that it's doable in a much more controlled way, and that a lot of nice things can come out from a lattice. So with that, I'm going to stop and thank you for your time and open the floor to questions.
Okay, thank you. Everybody virtually applauds. So there are a few questions in the chat. If people want to raise their hands, I'll unmute. And if there are other questions, of course, not in the chat. So maybe I'll just read
okay.
Question. So, well, let's see, Nati raised his hand. So go ahead, Nati.
Yeah, the challenge of continuum versus lattice is completely different when you discretize space or space-time than when you discretize the target space in quantum mechanics. So it's not clear to me how this thing is going to address it. And let me give you just one point of reference. When you talk about discretizing space and you discuss the continuum theory or the lattice theory, locality plays a fundamental role. Whereas in the target space, you have a bunch of points and you have some coupling between them, and locality doesn't, well, it means something, but it's not as fundamental as in the other case. So I fail to see how this advance, interesting as it is, can address the question when you discretize space.
Okay, no, that's a fair question, and I guess I really didn't say anything technical about how this set of ideas extends to higher dimensions, which is true. Basically, right now at the level of, given the amount of stuff I was able to say in this talk, you have to take it on faith that it is possible that related ideas can be done, can be implemented in higher dimensions, and then it sort of take a second talk for me to describe them. I kind of told you some of it back in the day, a few months ago when we talked informally, but yeah, there is an entire other set of things that you need to do to generalize to higher dimensions. It's inspired by this, so it's morally similar. But yeah, I'm not pretending that everything I said today is enough to generalize to higher dimensions. There's a few more ideas that are needed. So let me just say that, and then if I'm happy to either give a secondary talk or explain in much more detail later how you do this in higher dimensions. I will say one thing though, that this is that doing this target space smoothing is important if you want to talk about scalar theories in higher dimensions, because there you will need to have a notion of being compact in the target space, in addition to being smooth in some appropriate sense in the spatial directions as well. So this is a vital ingredient of properly smoothing QFT in higher dimensions, but it's not the only necessary ingredient. Let me put it like that.
Let me ask if you do.
I still don't understand the answer. So,
well, okay.
So you talked about Zn and say S1 for the target space. So we can do the same thing, say, in 1+1 dimensions. And there, the issue is not really the discretization of the target space, but discretization of space. These are really two totally different issues.
Yeah.
Okay.
Yeah, they're different. So you will have to, so there will be a separate discretization of the target space, which will be relevant if you have a scalar theory, and there will be a separate discretization and the related issues of smoothing along the spatial direction. Absolutely. So these are related but not the same. And I'm basically postponing the complete answer because I don't want to hog another 20 minutes here. But yeah, I'm totally agree that these are different things and you need to keep track of both.
So since I have the floor, I might want to ask another follow-up on that, and then I promise I'll shut up. Oh. So imagine you're interested in SU2 gauge theory.
Okay.
Or some other non-abelian continuous group. You can't discretize it and get a nice limit that approaches the, say, SU2.
Yes.
So, and in fact, you don't need to, because you can keep it SU2, you can keep it continuous on the lattice. So I think you're kind of addressing not what the real question is, but another question, which doesn't even arise. And now I'll keep my promise and shut up.
Yeah, I mean, I would say that the question that I'm addressing arises when you study, when you try to talk about things like, I agree, it arises when you talk about things like U1 theories, when you try to, for instance, when you try to do abelian bosonization, this is a kind of question which may arise because you want to say, okay, if I ask you what is the analog of abelian bosonization on a lattice, we know from the continuum that it's some kind of compact scalar on one side, and on the other hand, it's some fermion. So if you want to be very precise about which degrees of freedom actually map, you will end up doing some kind of smoothing like this in the target space, in addition to doing various things in the spatial direction in your 1+1 dimensional QFT. I agree. And then, so in that case, the stuff that I talked about will be relevant. There will be other cases. So basically, anytime you have an actual Gaussian scalar, or like a U1 target space, this will be relevant. Of course, when we talk about the really juicy things, we will have non-abelian target spaces, for which I agree, like this will be more complicated and there will be other issues involved as well. I'm not pretending to have covered them at all in this talk. So let me just say that there will be similar ideas, and I will be giving eventually, presumably, more talks on those details. But I'm sort of having to divide and conquer. Yeah, we can.
Okay, well, maybe that's a good point to say that the next talk in this series will be in 2 weeks. It'll be Chris Beam from Oxford. And let's thank Djordje again. Thank you.
Oh, okay.